Frank Slazer. I'm the president and CEO of the Coalition for Deep Space Exploration, the organization that sponsors this Space 101 series. We're a DC-based trade association for the space industry. We've got about 50 company members, and we advocate on a variety of issues, both concerning member and industry issues, as well as trying to make sure that the United States remains a leader in space exploration, space science, and space technology development. Today's session is really an interesting one, really a really cool one. It's about human spaceflight design. And for those of you who are kind of following the news lately, there are probably more crewed space vehicles in existence right now and flying right now than there ever have been. It used to be just Soyuz and the space shuttle, and now the Chinese have a spacecraft. And then just within the United States, we have two suborbital vehicles, one by Blue and one by Virgin Galactic, and then we've got SpaceX, and soon we're going to have Boeing. But the one we're really here talking about today is Orion. They're not all the same. They face very different challenges in keeping people alive and healthy in their environments they're going to. And they encounter very different stresses to the vehicle itself and to its capabilities and how long they can operate in space and all these kind of different details. So the intent here today is to help people in the communications industry, broadly defined, to understand a little bit about what goes into spacecraft design. And that way, when you start seeing things happening like the Artemis I mission this summer, you'll be able to understand exactly what the mission's all about and what went into making that vehicle happen. So I'll turn this over to Gary Napier, who is with Lockheed Martin in Denver. He's going to be the moderator for today's discussion. And Gary, take it away.
Well, thank you, Frank, and thank you to the Coalition for Deep Space Exploration for putting on this education series. We're just really happy that we can play a role into today's session. So as Frank mentioned, we're going to discuss the differences between human-rated spacecraft that are developed for different destinations, low Earth orbit and deep space. It's an exciting time, as Frank mentioned. Right now in human spaceflight, we have quite a few vehicles in design, production, and even operation by both governments and private sectors that can take humans out to various regions of space. But there's often kind of confusion about the differences of these spacecraft and their capability. So to help clear that up for us, at least a little bit, are two experts on this subject. So joining us today is Najoud Moranci. She's the Chief Exploration Mission Planning Officer at NASA's Johnson Space Center in Houston. And also joining us is Tim Chehan. He is the Space Exploration Architect at Lockheed Martin Space in Littleton, Colorado. Thank you both for joining us. All right, so for our audience, thank you for joining us. That's actually why we're doing this. So we're going to start off with 4 or 5 questions, and then we'll open it up to you. You can submit the questions in that chat link right there below, and we'll try to keep your questions related to today's subject. So we'll probably go for about 30 minutes and then do 20-ish minutes of questions. And so let's just go ahead and get started. Najoud and Tim, can you tell us a little bit about your background before we kind of get into the questions? Najoud, why don't we start with you first?
Sure, thanks. Najoud Moranci, NASA Johnson Space Center. I started on the International Space Station doing guidance, navigation, and control years ago. Have also worked through on Orion program office, vehicle integration, things like that, and eventually now into mission planning at the Artemis level. So my office is responsible for architecture and mission planning across the beyond low Earth orbit portfolio for NASA. For a human spaceflight, not for everything. But in large part, that is primarily the Artemis campaign, beginning with Artemis I.
Kim?
Everyone. So I actually started as a trajectory designer for geosynchronous communication satellites. It was a great way to start. My first 5 years of my career, I was on the mission team for 15 spacecraft. But then I got the opportunity to join the Orion program. I spent about 10 years on Orion, first as a launch abort system trajectory person, did some system engineering rotations, and ended up being the Orion system architect at the end of that 10 years, which was a great way to prepare for my current role as space exploration architect for Lockheed Martin. So really leading the teams that develop our advanced concepts across all of the segments of commercial civil space, developing things like the Mars Base Camp concepts and lunar landers and a lot of other fun stuff. But Orion is really dear to my heart, and it's an amazing vehicle and a great challenge. We'll talk about some of those things today.
Good deal. Thank you both. So let's just jump right in. First question goes to Najud. So what do we mean by deep space, cislunar space, and low Earth orbit?
Yeah, great question. So, I mean, things can get a little confusing, but it's mostly defined based on altitude relative to the surface of the Earth. So, low Earth orbit is things that are still very much affected by the Earth's environment, magnetic field, heat, things like that. So that generally goes out to about 1,000 kilometers of altitude. So things like the space shuttle and the space station, all of those things fly very much within low Earth orbit. Cislunar is defined essentially from geosynchronous space out to the moon and the moon's relative orbit. So you're more of in a deep space environment there where you're not affected by the Earth's magnetosphere and heating and albedo and stuff. So it's a lot in the scale of relative distance from Earth where we draw these things. And so especially for Artemis, we're talking about those deep space environments in the cislunar space.
Tim, you've got a graphic, don't you, that can kind of put some of these into a relationship. Are you able to pull that up?
Yep. Let me share my screen here. So I put this together, and Gary, let me know when you can see it.
Yeah.
Cool. To have everything to scale, and so I might have to do a little bit of zooming in and out. But what you're seeing here is here's the Earth, and the yellow is the area out to geosynchronous orbits, and then this is the lunar orbits. And the lunar orbit actually is a little bit elliptical, and this picture is circular just for the ease of making a graphic. But you can see the scale of the distances here. And then as we zoom in, so let me kind of zoom in to Leo. So the blue is that 1,000 kilometers that Najud was talking about. And the ISS is a couple hundred kilometers altitude. So it's this red dotted line that you can hardly see because it's so close to the Earth. This one is the GPS orbit. And then here's geosynchronous. And so, a pretty big space here as far as distance. And of course, the Van Allen radiation belts are about, they're underneath this GPS orbit is the full extent of them. So pretty long distances here, which also means that from a velocity perspective, higher velocities, particularly when coming back for reentry.
Tim, I heard one of our engineers one time kind of do the metaphor of that if the Earth was a school-sized globe in a classroom, that the International Space Station, 240 miles up, would be about a quarter inch off of that globe, about a centimeter off of that globe. The moon would be 30 feet away on the other side of the classroom there. And then Mars would be 5 miles away. Can't even point to that. So I don't think sometimes we really grasp the distances that we're talking about to go out in cislunar space or deep space. So talking about that though, Tim, what are the differences between the environments of deep space and LEO that drive vehicle design?
Sure, and I sort of think of it in kind of three different big categories. One is the environment differences. So, how is the environment of space different between LEO and deep space? There's mission differences as well about, hey, we're going to perform a mission, we're going to go to the moon, and what are the things that are different there? And then there's infrastructure differences. So let me step through those. So from an environment perspective, we're talking about things like the radiation environment, the thermal environments, and even just the environment of speed. How much energy or velocity does the launch vehicle need to do to get you out to that area? From a radiation perspective, in low Earth orbit, the Van Allen belts are really protecting the astronauts, particularly from the galactic cosmic rays, as well as the proton events. And there is a higher radiation environment in LEO compared to the Earth, where we also have the atmosphere. But once you're in deep space, particularly from a health perspective, those galactic cosmic rays, the really fast-moving particles from the universe, are damaging. and then the proton radiation is also something to be concerned about, both for the people and for the electronics. So for the electronics, you need to be able to have a tolerance to radiation upsets. And if you do have a radiation upset, the total system needs to have the redundancy to be able to react to that radiation. And on the crew side, and we'll talk through as we go through the differences in the Orion vehicle and other radiation mitigations, but the structure of the vehicle and the storm shelter over Orion provide that protection for the crew. From a thermal perspective, when you're in low Earth orbit, there's a lot of heat coming from the Earth. And when you're in deep space, you don't have that heat source. If you're in low lunar orbit, there's a heat source there that's smaller than the Earth. But out in the transit between the Earth and the Moon, or whether we're in NRHO, there's no heat source from the Earth. On a mission perspective, there are a couple of differences here. One is that the Orion spacecraft spends in its current lunar mission weeks alone by itself. There's no International Space Station. There's no 90 minutes to get back to the surface of the Earth. The crew and the vehicle are on their own. And so that really drives a level of safety and redundancy in order to be out there all by themselves. And then another mission difference is reentry from lunar speeds. So coming back from the Moon, worst case is 11 kilometers per second. Where coming back from Leo is about 7.8 kilometers per second. And that speed coming back from the Moon means that there's a large temperature difference. 5,200 degrees Fahrenheit versus like 3,000 degrees Fahrenheit. So significant differences there in the mission. And given that we're going to the Moon, a lot of propellant is required to be able to inject into the lunar orbit, to be able to put yourself back on a reentry speed. So a lot more propellant's needed. And then from an infrastructure perspective, a couple of things. One, I mean, there's no GPS out there, so Orion needs to be able to navigate with support from the ground, and Orion also needs to be able to navigate without support from the ground, and that's a sort of a safety measure. So we have multiple ways to navigate without GPS, and that distance means that we need to use communication systems on the ground that are designed for those large distances, so like NASA's Deep Space Network, as well as the communication system on Orion needs to be able to handle the distance there. Oh, and I've got another graphic here that kind of goes through some of those differences. So we talked about the temperature difference and the speed difference, and the speed and the temperature distance actually impacts the reentry heating rate and total heat load. I forget whether they're squared or cubed and which one is which, but it's not linear for the heat shield that Orion carries as far as that environment from reentering. And then we talked about the difference in distance is huge, and that just drives everything into the design of a deep space vehicle.
Very good. Wow. I mean, there are a lot of differences, but the speed and temperatures and those distances definitely are big, interesting points. And this next question is probably for both of you. Maybe Tim, you can start it off. But how do those differences that you just talked about show up in deep space craft design in the actual engineering design? I mean, what are some other elements?
Yeah, and it almost touches every subsystem on the Orion vehicle. And so I'll throw out some of my favorite examples, and as you can chime in as well. So I mentioned propellant. So Orion's carrying about 8,600 kilograms of propellant. Most of that is for the return burn from the Moon, and so that's stored in the European Service Module. So and also from a propulsion perspective, so we've got the total amount of propellant, But we also need to be able to have redundancy for that large amount of propellant. So from a thruster perspective, we have the primary thruster and we have backup thrusters that even the backup thrusters are designed for this huge delta V that needs to happen. And then there's the attitude control thrusters, which also have redundancy. So that really drives the safety critical propulsion system, and also from a large capability perspective. Another example is the the carbon dioxide and humidity removal system. It is a regenerative system. We call them swing beds because there's what happens is a material that absorbs the humidity and the carbon dioxide, and then we expose those swing beds to vacuum. The CO2 and humidity leaves into the vacuum of space, and then that system is ready to absorb more CO2 and humidity. So it's not a commodity that we're using up. everybody, at least everybody who's working human spaceflight remembers that great scene in Apollo 13 where they've got, the CO2 removal canisters are square on one side and circular on the other. We don't have those canisters on Orion because that's a consumable, and Orion is designed for a much longer mission.
Hey, Tim, before you go on, can you bring up, you've got another graphic, don't you, that I think hit some of these?
Yeah, there it is. This one's just talking about from a consumable perspective. How much carbon dioxide needs to be scrubbed out? How much water do we need? How much propellant, food, oxygen, reentry speed, radiation environment? Everything is upsized, is a bigger sized for Orion. And go ahead.
I mean, let's just see if Najut can add on to that list. You were starting with a pretty good list. Any others that jump out to you that are of interest?
Yeah, I think Tim did a great job talking about sort of the spacecraft differences. So if you think about it from the mission design differences, though, there's a lot about going to the moon that is different from low Earth orbit, right? When you're in low Earth orbit, the space station, it's going around the Earth in a mostly circular orbit 16 times a day. So you have lots of opportunities. You launch when it's overhead. You can do it again the next day if it doesn't work. You can come home into the Atlantic or the Pacific. You have many orbits and opportunities to divert. One of the main differences when we go to the moon is, first off, we have to time our alignment to lead the moon, to enter the orbit, to do our flyby. So we're very constrained about how we get to the moon. We're launching from Kennedy. We have to get to the moon. You're timing it like a quarterback throws the football in front of the passer. All of those things have to happen. And then the criticality of the burns around the moon. We fly by the moon about 60 meters or 60 miles, 100 kilometers above the surface of the moon, and you're using the moon's gravity to start targeting burns. So a lot of those burns are occurring on the far side of the moon without comm with Earth. So we are automating them through software, which is an advantage we have that Apollo didn't. And then the crew is performing some very critical operations without the benefit of ground support. So a lot of our differences start coming in that resiliency and the reliability of being able to do things on much more constrained planning. So we have to do certain timing, targeting, things like that. You only get one opportunity to do that flyby. And if you don't, we have abort scenarios where we can do different burn types to get back to Earth. So when we talk about these moon mission planning, we actually have thousands and thousands of different trajectories to run through those scenarios based on what could happen and the timing. So when you're in Earth orbit, you get very predictable, very circular orbit type things. When we go to the moon, it starts being a lot of differences in the planning of how we get there, use the moon's gravity to insert into orbits, and then use it for aborts and contingencies. And then a lot, as Tim mentioned, right, it's the time. When you're at the space station, we can always come home within a few hours. If there's any major emergency, the crew is just a few hours from home. You need very limited commodities, as shown on this graphic, to be able to do that return. But when we're at the moon, we're always days from home. No matter how much prop you throw at the problem, you're days from home. And we need to be able to make sure the crew is safe throughout that time, handle the faults and contingencies that can happen, and plan all those orbit parameters. When we start going down to the surface of the moon to get home, the crew has to meet Orion back in orbit and then do departure burns and then come home, similar to Apollo did lunar orbit rendezvous. We're using different orbits, but all of these things have to be planned and coordinated across the vehicles. And it's a very different type of planning than people are used to with what is happening on Space Shuttle or Space Station. So a lot of our differences aren't just in the physics of the spacecraft, the physical differences of the spacecraft, it's the physics of going to the moon and the orbit mechanics associated with it.
Very cool. A lot of consumable differences, but also the speeds. And speaking of the speeds, and Tim, you kind of touched us on a little bit, but this question could be for either one of you. Talk a little bit about the heat shield, the way that we're doing reentry. Maybe even talk a little bit about skip reentry.
Sure, yeah. So skip reentry is the capability, when we come in, we start our reentry profile, and the atmosphere slows us down, but we have control with the capsule in order to point the lift vector. And actually, let me get one of my little models since I actually have it here. So we've got the capsule, and the CG is offset a little bit. And that offset in the CG means that there's a tiny little bit of lift vector on the capsule. And so when you roll the capsule, you're pointing that lift vector. So Orion is determining its speed, it knows its lift vector, and it actually skips a little bit. So it goes into a deeper part of the atmosphere, it comes up, and what that allows us to do is to precisely control a much longer reentry corridor, but also steer the vehicle. And that allows us to have a very accurate touchdown point, especially compared to Apollo, where we can land close to the coast off of San Diego, much closer to the rescue forces and the recovery forces that are coming to get to the crew. So skip reentry is a great safety feature. And then from a speed perspective, the Orion heat shield is using AvCoat, which is an ablative material. And why we like to use ablative materials is they suck up a lot of heat, and then when they ablate away, when the pieces of the heat shield ablate away, they are taking that heat away from the vehicle, such that it doesn't soak back into the vehicle. When a capsule lands, the peak temperature for some of the components are actually an hour or maybe even 2 hours after we land, because all that heat is still coming from the heat shield and coming through the structure.
That's amazing. Even though it's sitting there in the water, that heat transfer is still going on for that long.
Yep.
You mentioned heat shield and the skip reentry being kind of a safety. Talk about the top side of the vehicle from the launch abort system and kind of the difference in the size of the launch vehicle and the launch abort system and the need for that.
Yeah. So so this is the model of the LAS, and we've got a large solid rocket motor here with it's actually here, and the exhaust comes out these nozzles, and then there's an attitude control motor at the top, and so that gives us active control over the LAS. And what it allows us to do is to get away from any issues that are happening on the launch vehicle. And the speed that we need to get away from the launch vehicle is really determined by how much energy the launch vehicle has. And so for SLS to send us on a direct trajectory to the moon, it's a big launch vehicle. It has a lot of energy. And so the launch abort system for Orion has to be large enough to get us away quickly, and also it's quite a dynamic environment. There's a lot of aerodynamics and acoustics going on. We could be aborting from the pad. We could be aborting when we go to Mach 1. We could be aborting higher up, and that system has to be able to maintain control through that whole range of things. And that's what the Orion LAS does, and gets us away from any kind of issues so fast.
Good deal. Najid, anything you want to kind of insert in here? Some other unique differences that maybe we haven't touched on yet?
I think one of the other unique differences is really centered on the human, right? We're taking humans to the moon. The exercise they need, I mean, these are long missions, well away from Earth, in very small vehicles comparatively to the space station, which is the size of a mini room apartment. So they can have lots of exercise equipment on board the space station. We need to use very compact exercise equipment, but we also need to make sure that the crew's maintaining their health, their bone density, muscle mass, things like that, because not only are we going to space, but then they're going to be asked to go down to the surface and perform work in a lunar gravity environment, which is less than Earth, but still they need to be able to be fully adapted and ready to go to do those EVAs when they get to the moon. So we do need to worry about the crew, make sure they're safe and healthy through exercise, all their food, the systems they need throughout the mission, as well as to keep them healthy in transit to do operations in a gravity environment and then healthy again on their return home. So there is a lot of complexity here. And these are longer missions, right? The longest Apollo mission was, if I'm remembering correctly, around 11 to 12 days. But we're looking at doing many weeks of mission and eventually months of mission. So you need to be able to have all those systems built in and all that experience we've learned on ISS that we can apply to this lunar environment, as well as supporting EVAs down to the lunar surface and doing exploration on the moon.
And since it's a closed system, everything interacts with everything else. And so the heat and the humidity that's generated by a crew exercising then has to be accommodated by the life support system to be able to keep the temperatures right, keep the humidity right. And so, you know, one problem we solve over here shows up in another place. And through the Orion's development, we've worked through all of those issues so that the integrated system is capable of doing the mission.
Can one of you talk a little bit about redundancy? You know, you talk about like these planetary vehicles that are going out to Jupiter or Mars or such. They usually have like an A and B side avionics, and that's kind of it. Some of them are even single stream, but maybe talk a little bit about the redundancy of an Orion comparative to like a low Earth orbit vehicle.
Sure. And so from the perspective of being alone, for weeks at a time, and also, doing from a mission perspective, some things like, we go right through the Van Allen radiation belts right before reentry. There's not really time to have a long recovery there. So we've got to set up everything to have that reliability and redundancy. So the avionics for Orion, the prime avionics system, that it's redundant, and it's in a hot redundant system where there is no delay if there's a failure or a radiation reset. Everything's hot, and the systems all know to listen to the right commands. And if one drops away, it just keeps going. Doesn't even really need to think about it. So that's the prime system. Then we also have a backup flight computer with dissimilar software that can do all of the critical parts of the mission, in some cases in a simpler way than the primary system. And then we also have and this is outside of the normal reliability analysis, we have the manual backups to the backups, the switch that you flip that deploys a parachute, no software involved. And we have that set because one of the things about planning deep space missions and planning missions in the difficult environment and planning for decades of operation and the Orion being plugged into different situations like at the Gateway or part of a Mars transit system. We don't know what's in store for us in the future, and so we want to make sure that we've got a lot of flexibility and a lot of different paths of redundancy to handle anything that comes up.
I'm going to ask Najud to get into the mission maps in just a minute, but I got one more for you, Tim, or Najud, you can jump on this one too. But two things: radiation shelters and kind of how we deal with radiation, both from maybe a spacecraft, but also waste management system. I think that's one that it's got a little chuckle factor, and we don't always talk about it, but not even all human spaceflight vehicles even have a waste management system. Some of them do, and there may be less robust, or the capacity is different. So maybe talk about those two sides, and then we'll jump into the mission maps.
Sure. So from a radiation perspective, the Orion has a storm shelter concept built in and so this is a case where, hey, there's been a solar particle event, and we have warning systems that give us enough warning, and so the crew can get into a part of the Orion spacecraft that's kind of a little bit buried in the spacecraft, where there's a lot of metallic structure and equipment surrounding them, and that mass provides the protection from the radiation. So that's in the case of a solar storm. We also have a whole set of radiation sensors in Orion to understand what the radiation environment is. And one of the things that we're experimenting with is radiation protection vests. We're doing an experiment on ISS with that vest, and there's another vest that's flying on the Artemis I vehicle. So that we're also, looking at how do we protect from the radiation in that long distance perspective. And then on the waste management system, the space toilet, the reliability of that device is really important from a health perspective, very important, and also from being on a long mission and having that work is really important for feeling that you are healthy. And so we put effort into making sure we've got a very reliable, simple system that's small and compact. And Orion is a capsule; it's not a very big vehicle. But that system is very critical, just like any other system, and we put the same importance on that.
Good deal. Excuse me. So Najud, can you bring up the mission maps and talk about Artemis I, the mission that's just months away, and then also kind of compare it to the Artemis II mission map?
Sure, thanks, Gary. Yeah, so Artemis I, and as we look at these mission maps, you'll notice they are very, very different between them. We've drawn the trajectories, and it's a little confusing. The trajectories are drawn in Earth-Moon rotating frame. So if you drew a line between the Earth and the Moon, this is what it looks like, but all of this is happening while the Moon's going around the Earth in reality. But on Artemis I, this is an uncrewed test flight. So all of the mission design was essentially set up in order to fully test the exploration ground systems, the Space Launch System rocket, and the Orion spacecraft. And being uncrewed, we could actually stretch the mission duration out even longer than what would normally be there for crew on board, because without the crew, we can just keep testing systems in that deep space environment. So in this particular mission, we're launching from Earth, so that's the green line that begins at number 1. On SLS, we go to 1 rev in low Earth orbit. It'll drop us off, and us, in this case, Orion, off an ICPS upper stage at a 975 kilometer altitude at the apogee, so the highest point above the Earth. We're doing that 1 rev, and then the ICPS at number 6 there performs the translunar injection and sends Orion and the CubeSat deployments out towards the Moon. Once on its way, Orion will perform the remainder of the mission, which includes a flyby of the Moon at number 9, and then insertion into a distant retrograde orbit. So a distant retrograde orbit, it is distant because it's very high altitude from the Moon, about 40,000 kilometers. I'm going to remember my units correctly as I say this. And that orbit is retrograde because it's moving opposite the direction of the Moon. So the Moon's moving left to right in that picture, and Orion's moving the opposite way. So that's all that DRO means: high altitude, opposite rotation. But this orbit is a really high stable orbit. If Orion sat there and did no burns, it wouldn't leave the orbit for literally hundreds of years. So it's just a nice stable orbit with not cislunar, deep space environmental conditions that we can do all of our test and checkout. Literally, we're going to collect weeks worth of data overall from beginning and end of the mission. We can spend either half a rev there, so we go from 10 to 12, or we can spend 1.5 revs in that orbit on this mission. So go all the way around once and then pass 10 again and go to 12 before we leave. The reason for that is because we're actually setting up the entry conditions back at Earth, number 17, because we want to be able to collect extremely high speed camera data on the parachutes. So the forward bay cover jettison, the parachutes, and the splashdown, we want to do that in daylight. So in order to set up the right orbit mechanics, we actually have different length missions depending on the day we launch, between 26 days and 42, to set those conditions up. The differences in the mission length are somewhat in the inbound and outbound times of getting to and from the moon, but primarily how long we spend in the DRO, that we just stay in the DRO until we'll get the right landing conditions. So all of this being that flight test was set up in order to collect data throughout the whole mission. So we get a minimum of 3.5 weeks, but potentially up to 5 weeks of flight data, depending on the day we launch. And that's all literally the day of launch dependent on orbit mechanics, what determines that, to collect data throughout the flight. So we'll be able to test tip to tail the ground systems, the rocket, and Orion for the multiple weeks on Orion to collect that data, as well as deploy the CubeSats along the way. So this mission was designed around that uncrewed flight test opportunity. If you go to Artemis II on the next slide, very different conditions, because now we have crew, and this is the first flight of the environmental control system and life support. So the waste management systems, the swing beds to remove carbon dioxide. So very different test here. We're actually not stressing Orion vehicle, but are using it to demonstrate all of those crewed systems, as well as achieve some other objectives I'll talk about. So you can see this is a very different layout of trajectories here, designed around being the first crewed test of the vehicle. So we will test a lot of those life support systems. The ISS is doing demonstrations. We have a lab on the ground running it. But without having people on board on Artemis I, you wouldn't actually have anyone breathing carbon dioxide to remove. So you wouldn't even get a lot of the test checkout, even if we put them on Artemis I. But this mission is designed around testing out those life support systems and the crewed systems, the exercise, all of those things in a little bit less risky way right up front in the mission. So in this case, very different. SLS is going to launch ICPS and Orion into a high Earth orbit. So that's the green elliptical orbit there at the top of the screen Tim is tracing. This orbit is very big. The apogee is somewhere around 70,000 kilometers. So very different, very high altitude orbit. And it's a 24-hour period. So we will actually spend one day just doing one revolution around the Earth in this orbit. And that gives us a chance to test the life support and crew systems while we're still around the Earth. And if we have any emergencies, we can do a shorter abort and return to Earth. Hopefully not, of course. But if everything checks out in that first 24 hours, then Orion will perform at number 9, the trans-lunar injection, and do a free return flyby of the moon. So Orion will perform TLI. Once we pass the moon, just like you saw in the movie Apollo 13 we mentioned earlier, we use the moon's gravity to slingshot back. So for the whole rest of the mission, Orion is only doing minor course corrections, targeting, things like that. We can do those with just the attitude control thrusters if we needed to. So this is a very benign flyby of the moon, risk-wise, but we do send the crew out into the deep space environment. They get to test all the rest of the systems. So we are putting this together intentionally to do a crewed flight test out of it. So very different setup, but there's also a lot of some other demonstrations. So we're mitigating risks wherever we can. So at number 6 there in orange, we actually, once Orion separates from ICPS in the high Earth orbit, we'll do a proxops demonstration. So the crew will actually take the stick, the systems are on, and we'll do some approach and back out maneuvers from ICPS to demonstrate that near field proximity operations we'll eventually need to do when we dock to other systems. So this was a really good target of opportunity to add some objectives to the flight. They're not critical to the rest of the flight plan, but we do get to do some of that sensor data that we'll need for later missions, do some of those operations. It's really important when the crew is flying that they have something to look at, so you can actually test the relative approach and stuff. So there's a lot of stuff we can do in this flight, which are risk mitigations for later missions, as well as being a very different design for that crewed flight test objectives. So you can see the two differences there in brief on these crewed test flights.
Wow, fantastic. I didn't realize there was such a big difference to them, but that was really a good explanation. All right. Hey, let's jump into Q&A from the audience. Thank you both for really good primer on all of that. Marcia Smith, and I think Marcia's still online, she wrote that deep space used to mean beyond the Earth-Moon system, such as Mars and out. But if deep space OS being redefined to be synonymous with cislunar, if so, what are you calling the rest of the solar system? So kind of what is cislunar deep space?
So I don't think we're trying to redefine deep space. I think Marcia's correct. It's really beyond the moon. But in this case, if you're not near the Earth or the Moon, you're operating in deep space-like environments. So if you're not collecting that albedo, the heating and stuff from the Earth or Moon, the environments are otherwise similar to when you're flying to Mars. So a lot of this is that sort of Mars space, if you will. If you're transiting in deep space, we can achieve those same conditions as long as you're not near the Earth and the Moon.
Good
And
deal.
Tim, I don't know if you want to add anything.
Yeah, go ahead, Tim, if you want to, or.
No, the only thing to add is that, and in particular, that radiation environment, whether we're in DRO or NRHO or transit, is the same as when we're in transit to Mars.
Got it. All right. So talking a little bit about that, Rich says, hey, regarding the exercise requirements, radiation, Orion is small. Would it make sense to add a step to the Earth-Moon or later the Earth-Mars journey, such as launch to an orbit, transfer to a larger, maybe better shielded interplanetary vessel, trek to the Moon, transfer to a lander, and then reverse it all the way back. So Tim, I know you've worked on a concept we call Mars Base Camp. And I think some of that would make sense. Maybe talk about, do we need these bigger systems just to get to the Moon from an exercise radiation shelter requirement just to get to the Moon? And then talk a little bit about the going out to Mars, how Orion could be used to go out to Mars.
Sure. Yeah. And I think that for going to the Moon and for missions by itself of weeks and transit times of a couple of days, we've proven with Orion that from an exercise requirements and radiation requirements, we are meeting all of NASA's requirements for that, and we're doing that in the size of Orion, no problems there. When we talk about being in space for a year, or maybe 6 months to a year, I think that's kind of the place where we're going to want to have more space, to have better exercise, a little bit more radiation protection, and that's now we're talking about things like the gateway if we're in a lunar orbit mission or a habitat on the surface of the Moon. That's about the right transition time. And then there's a whole nother transition to going to Mars, where we're away from the Earth for 2 to 3 years. In that case, we want to have the larger habitat. We want to do things like we've done in our Mars Base Camp concept, perhaps where we have the one of the crew habitats surrounded by propellant tanks. Hydrogen is really great radiation protection. And we want to have the types of health, medical, exercise equipment that we're testing out on the ISS today for those multi-year Mars missions. But in lunar space, Orion is the right tool for the job.
Yeah, I'd say Orion is the upsized, better designed and shielded vehicle to get to the Moon. That's the whole purpose of Orion.
I like that. Good clarifier there. So Eric is saying, hey, y'all, thanks for doing this. And thank you, Eric, for joining us. So 2 questions. First, as you mentioned long duration flights in terms of requirements, how long can Orion fly on a mission to the gateway? And where would it dock for a while and then come back? So how long? And then number 2, how are you ensuring that you get the ECLSS data, the Environmental Control Life Support System? How are you ensuring you're going to get that data you need from Artemis I for Artemis II if a lot of those systems aren't flying yet?
Yeah, so I'll take that one. So when we talk about lifetimes of the vehicles, right, there's one amount, which is how long is the crew on board for which you have consumables, right, the oxygen, the water, and things like that. Orion has 21 days worth of consumables for 4 crew. So if you had fewer crew, you can stretch that out. If you added more in some way, you could lengthen it. But so there's 21 days of crew time on Orion, but Orion itself is certified for an additional 6 months of uncrewed operation. So when you start saying we're going to go to the gateway and do longer missions, Orion, with no changes to its current design, could stay there for 6 months. It would be docked to the gateway. In most cases, you dock, the crew would get out, be in the gateway, go down on the surface in the lander, things like that. Orion would stay attached to the gateway throughout that time, and really just does maintenance of systems on its own while it's there. And then the crew would get back in and come home. So we divide up the 21 days essentially of crew commodities on outbound and inbound, but you have a very significant capability for the uncrewed dwell time, if you will. And with some minor tweaks, you can even extend that longer. It's how much are we certifying up front.
Yeah, it's really about certification as opposed to capability. We've done an analysis of, with the current systems as designed, how long can they go? And they have all these reliability and redundancy requirements. And we showed in that internal analysis that we're good for the 1,000 days to go to Mars. There's a couple of systems that are not considered consumables for a lunar mission, but we want to change out some filters and a couple of things if we were doing the 1,000-day missions. So there's the capability of what Orion can do, but as you point out, what we're required to do and certified to do is all the way out to the 6 months.
And for the second part of that question on the life support data, I mentioned a little bit of that before, but I mean, the amine swing beds, which is essentially a new technology that had been developed for testing, which is the carbon dioxide and humidity removal, those have been flying on the space station for, gosh, I think at least a year, if not longer, probably longer at this point, because I can't do time with COVID anymore. But those have been in operation on space station. I think they work so well, they kept using them. I don't remember the name of the experiment, but certainly it could be looked up. So we're getting flight data on some of the systems. And then, like I mentioned, we have a test lab on the ground that is doing the whole, integrated Orion system, ensuring it operates. And then, of course, as I mentioned, we designed the mission differently because we are not flight testing it with crew before the Artemis II mission.
Good deal.
That combination of ground tests and ISS tests are getting everything we need.
So we've got about 10 more minutes before we wrap up. Got a couple more questions, and just remind folks that you can just type into the chat and we'll get to them. Next one's from Irene, and she says, in light of the growing capabilities, offerings, and interest of the commercial space sector, what flexibilities or new technologies can Orion bring to the table?
I mean, that's a really interesting question. I think the most important thing Orion brings right now is it is a certified cislunar transit and return vehicle for the crew. So a lot of that, like leveraging, there was an announcement yesterday on the second HLS vendor, right? It's what can we do at the moon once we get there? So I'm really excited because we need to get there, and now we can start doing all sorts of different missions. Having these vehicles, I mean, it's in the name. As much as cheesy as it is, Orion's official program name is the multi-purpose crew vehicle. And to me, that multi-purpose as the mission planning team is we can do very different missions now that we have the system available. None of the NRHO wasn't even considered in Orion's original requirements, but we've completely redesigned the missions, and Orion is fully capable of doing it. So the flexibility that Orion brings us is a lot of different missions. So whatever systems you bring online, we'll figure the missions out that you can use them. So there's a lot we can do with Orion, exploration-wise and architecture-wise, now that the system is out there.
Ryan, Irene has a follow-on here. I don't know if it's a little out of the swim lane topic of our discussion here, but it says, could you also talk and address the alternate NASA pricing structures and possible customers for Orion and Orion-derived technologies? Does anyone want to take a stab at that? And if not, we can just follow up with Irene.
Yeah, just a couple of points there. One is we've moved past the development contract of Orion into the production contract. We've evolved that contracting relationship, and we've baked in flexibility as we move forward to get to the low cost production and to have the right contracting structure for that. So working with our NASA customer for that. And then as far as Orion derived technologies, as an example, from a Mars Base Camp perspective, the specific technologies, whether it's the swing beds or it's the crew displays that, can take a LAS abort and a deep space radiation environment and be intuitive to use, or whether it's the Avcode heat shield or the parachutes, those things can be applied to future deep space vehicles, whether they're lunar landers or whether they're Mars vehicles, or as Najib points out, we're not quite sure what the future will hold, but both the Orion vehicle as itself plugging into these different architectures, it's got so much capability, that we can just do that. And then the individual technologies will be applied to those future vehicles.
And Tim, I assume with Orion, we can also, I mean, it applies to HLS, crew, cabin, crew systems. I forget what the new one is. It just got named the other day, the Sustainable Lander. So those are Orion-derived technologies absolutely could be applied there, right?
Yeah, absolutely.
So let's get on over to Gene says, thanks for doing this. He says, for the Artemis I mission extension to 42 days, what would be the call to extend? And are there any dynamic maneuvers planned where you really wouldn't want to perform with the crew on board? Basically, how hard do you plan to push Orion on Artemis I? It's kind of cool.
Great question. So it's not so much a call to extend the mission. It is on the day we launch, how long the mission will be is already determined. So whether it's, June 11th or 12th could be a different length mission. So when we launch, that's already pre-planned and pre-known. So for the nominal mission design, that length occurs, I have calendars that show on this day it's this length mission, on this day it's this length, and you come home on that day. That's all preset in what we've done with trajectory design. The only calls that would occur is if during the mission failures or contingencies occur, we have bailout points throughout the mission. So we can end the mission early, but how long we nominally plan to fly on any given launch day is predetermined. So that's it's not a debatable thing when we launch. But we can return early throughout the whole mission, if failures occur. And we actually have a whole bunch of alternate missions. So if something had happened with ICPS, we can still get a bunch of flight test data out of Orion flying around the Earth longer. So we've tried to design in as many points as we can to continue collecting data and get as much out of the flight throughout a series of contingencies without just aborting and coming home. So there's a lot in the mission design for contingencies underneath the nominal that you just won't likely see, because we've got so many different contingencies. We hope to go down none of those paths, but if they did, we've got plans in place. I think the second part of that question, I'm looking right. We're not pushing Orion in a sense of doing anything we wouldn't want to do with the crew on board. The maneuvers around the moon, the insertion into DRO, and the departure, all of those things are exactly, for the most part, like they would be on future missions. The pushing in this case is we just get to fly a longer mission. We have flight tests planned throughout, so we'll fly some, not nominal attitudes to collect power and thermal data differently. So we can do a few things that are just more data collection, not really pushing the vehicle and risking breaking it in some way.
Very cool. All right, Marcia, kind of following up from our cislunar deep space theme, she says, I would have thought that deep space, for example, Mars version of Orion would be different from a cislunar version because of the duration, but I just heard Tim say Orion's good for 1,000 days. So once Orion flies on Artemis II, is it certified for Mars also? And I will say, Tim?
Yeah, and so it all hinges around that word certified.
Yeah.
So from an engineering perspective, certified means we have requirements, we've designed to those requirements, and we have a detailed verification plan of analysis, test, demonstration to do that. So we are certified for the moon. We've done that process for the moon. And then we've analyzed, could we do 1,000 days? And there's a couple of poke outs, and the answer is in general, yes. So what that tells us is that if we decided to add Mars requirements to Orion, the vehicle as it exists today, for the most part, we would do an analysis in a verification plan and show that we were certified. But we haven't done that step yet. And that Artemis II flight data will be a big part of the verification rationale when we get to the step of certifying for Mars. But we haven't done that. But seeing the analysis gives us the confidence that we could do that certification in the future. And then all kinds of complexity comes up on Orion going to Mars. The reentry speed that's worst case for the moon is the best case for Mars, so we could reenter in the best case. But there's then it all depends. It even gets, Nuju's been describing the complexities of trajectory design just to go to the moon. You can imagine the complexities of going to Mars. And so there are reentry speeds coming back from Mars. that we would need to do some upgrades on Orion. There would be changes there. And of course, Orion, you never send Orion to Mars with crew because it doesn't have the storage space for the consumables and things like that. It always would be part of a bigger system.
I think that's important. I think it's fun to always talk about Orion going to Mars and do these analysis and studies and concepts. But I bet Naju's going to say, hey, we've got a lot of Artemis missions ahead of us, right?
Yeah, we got a lot we can do around the moon, and I'm excited for that.
Cool. Hey, folks, I mean, 3 minutes till the top of the hour. I think we kind of ran out of time today, but well, I really want to thank our audience for tuning in and asking some really good questions. We absolutely appreciate those. And, you know, if there are any questions that you still have and we didn't answer, please pass them along to us, either myself or Frank, and we'll be happy to try to answer them. I want to thank Najud and Tim for taking time to explain today's topic. I just thought it was fascinating. I wish we had another hour. So thank you all. Let me hand it back to Frank to close out today's session.
Yeah, a couple of things. If you have any colleagues you think might benefit from having been here but who couldn't make it, the video of this will be available on our website in a day or so, and you're more than welcome to review it again if you didn't quite catch something or had another question you wanted to follow up on. We're going to keep doing this series for a while yet. We've got another one set up for April 14th. We're going to be talking about humans in space, and we're going to have a rather perfect expert on that, a guy named Charlie Precourt, a former NASA shuttle commander, NASA astronaut, and Northrop Grumman executive. And he'll talk about humans in space and why people are going to be in space and what we can achieve with them there. And then on May 6th, we've got another one lined up. We're going to talk about the Gateway. There's a little bit of talk about the halo orbit and where Artemis is going to go. Well, the Gateway is where it's going to meet up with the HLS and go down to the surface. So we'll have more information about the Gateway and what's being planned for that, the international cooperation being planned for that. And we'll talk about that in about 3 weeks, maybe 2.5 weeks, more like 5 weeks, anyway, May 6th. So thank you all again for joining us here today. And thank you especially to our speakers. You guys did a great job with us and really appreciate your support. Bye. Thank you.
Thanks all.